Okay, so this is our video for project 1 of CECS 346 at CSUOB. The project is the table traffic light and advanced controller using a more finite state machine. And before I show the code actually working on a breadboard along with the Tiva Launchpad and everything connected, I'm gonna try to explain the code a bit and see if I could get everyone to understand what's going on here exactly. So before I continue though, I'll point out these comments here that essentially just show what everything connects to between our board and the Tiva Launchpad. Also, I'd like to apologize if there's any noise in the background because, of course, this is recording from home. This is a recording from home, so I can't really help but understand that there's going to be noises in the background, essentially. Okay, so I'll continue now. So we did use the systic.c and systic.h files that were provided to us in lab 3. And also there is a difference here. So in the project 1 handout, it was recommended to us to use certain ports, for example, PA2 and PA3 for inputs and PF4 for a right turn input. But we actually ended up switching that because we found it difficult to have 2 separate ports as input while also using a Moore machine. So instead of doing that, we decided to completely scrap PF4, which is switch 1, and go with port E port E for all 3 of our inputs. So basically, this is our declaration for port E, which are our inputs, port B, which are our output LEDs, and port F, which is the RGB LEDs that are built onto the Tiva Launchpad. And here are our prototypes, and this is the systic wait 10 millisecond function from the systic.c file that was provided to us. Finally, before I go into the actual body of the code, we defined these variables here, which it was clued to us through the code that was already provided on the project 1 handout. So we changed it up a little bit, of course, so it could match port B and port F, and the sensor is essentially our port E inputs. So yeah, so these are our definitions to receive a code for the output of the LEDs, and same for port F, but onto the Tiva Launchpad, and the sensor for the port E inputs. Okay, so the actual body of the code. So first we have the struct. The first variable essentially matches the RGB hex code for the LEDs that are built onto the Tiva Launchpad. The second variable are the LEDs that are the second variable is the variable that is going to read the hex for the LEDs that are built onto our breadboard by us. Next we have time, which is essentially our delay. And finally we have the different states that each state can actually go to. So the Moore machine. And then we defined each name with a number which corresponds to the position of the array here, 0 to 5. And yeah, so finally we get into our main and our actual while loop. So again, it was mentioned in our project 1 handout that we're starting with the green LED from east to west on, and the red LED for both the right turn and the south north off, or on, sorry, for the red LED. So yeah, so I could finally now show you, oh, down here actually, we have all of our declarations for each port. Yes, I mean, I guess I could show that we decided to unlock PF0 just because we're following lecture notes, and it was unlocked for both the friendly and unfriendly initialization of port F. So that's why we decided to unlock it here. Okay, so now I can finally show the breadboard, which is right here, already connected, and as I mentioned, go east is already in the on state, while both the red LEDs for both right turn, which is on the Tiva Launchpad, and the positive logic up here for south north red LED is on as well. Also, this is negative logic here, so that's why some of our hex codes seem a little bit different. That's because 0 here corresponds to the on state, and 1 up here corresponds to the on state. So that's hence the weird maybe hex codes that are in our Moore machine. Okay, so first I'll show that the LEDs do change for when when I guess I click on south north, so that's up here, P1. And if I, sorry, I'm looking through my camera, so if I flip that on, this should go to green, but before it does that, this will go to yellow, then red. So let's show that first. So this is on. There it goes. There you go. So it is now, go north is now currently the state that the Moore machine is in. And I can actually show that if I quickly switch back to here. So we're starting at go east. Go east is 2, so we're on the 3rd line here, right? So we flipped on we flipped on the south-north switch, which means that the position would be 0, 1, 0, and 0, 1, 0 if we follow. I'll quickly go 0, 0, 0, 0, 0, 1, 0, 1, 0. So it goes to wait east from go east, which is correct because wait east is our yellow LED from east to west. So that's the next line. So 0, 1, 0 remains because that's those are essentially the switch inputs that we currently have on. So wait east is 0, 1, 0 is here, which is it's the 3rd position essentially. Goes to go north. So go north remains in the go north state continuously until another switch goes on and the state, you know, can finally move on from that. So we can see that that does follow. It didn't go north. So the green LED for go north is on, red LED for west is on, and the red LED for right turn is on because the right turn switch is not currently flipped on yet. But if I do flip that on, which I can show, so actually maybe to show that the Moore machine is working. So before I flip that on, I'll show you what exactly the state should go to. So currently it's 0, 1, 0. So if we're going based off of a binary, then the next state will be 1, 1, 0 because you're going right to left on bits. So 1, 1, 0, that corresponds to the second to last position of go north, which is our turn. So if we go to our turn, which is this line here, and yeah, so our turn. So it'll continuously stay on our turn with the green LED for the built-on LED on the TiVo Launchpad on green, and then 1, 9, which is essentially the same as up here, which means south-north is green and east-west is red. So yeah, so essentially you're going to expect it to go to our turn, and our turn is going to continue to stay on our turn until another switch is on, which essentially just means that the green LED, that red LED there, will go green. So let's try that. So this is the switch for right turn. Flip that on, and there it goes. It did flip to green. So the state, again mentioned, is currently in our turn, which is our variable that we defined, and in our Moore machine, it'll be continuously staying on our turn because the input is 1, 1, 0. So I'll show that again. 1, 1, 0, which is the highlighted portion there. And I'll show that going off now. So if I turn that off, it'll go back to 0, 1, 0. And 0, 1, 0 is the 3rd. So it's essentially it's this one. So it goes back to the TiVo Launchpad LED being red. And yeah, so it should go to go north. And go north should continuously stay on go north because 0, 1, 0 is the current input. So if I flip that off, so the green LED should go red essentially. There he goes. So we can see that our Moore machine is so far working correctly. I guess the next thing I'll show is so we'll turn west back on. So we'll turn south off, turn west back on. So this will go yellow up here. There it goes, and this should turn green next. Well, that goes red. Yep. So again, that is our Moore machine working correctly. So the next thing that I'll show is that having the right turn on, it does make the south-north LED green go on, and so does the right turn. So if I show that now, there it goes. So that wait time there, it was the 8-second delay for a red LED. Oh, it's actually cycling. That's right, it's cycling because west is also on. So that's also another another possibility of our Moore machine. So I mean, it'll cycle through everything with the LEDs being, I mean, sorry, the inputs being on like this. Again, this is a requirement of Project One. It is showcased in the Moore machine. I mean, I could show every state, but that will make the video quite long. It's already 10 minutes, so it is pretty long already. But essentially, what I've just shown is that the Moore machine, hopefully, I've just shown this, that the Moore machine does work. Again, I could prove that every single state here works with a long video, but I don't think that would be the best way to showcase that. The best way to showcase that would probably be just to show this cycling through everything. So I'll show it one more. I'll show one more cycle. So keep an eye on that red LED on the right turn, which is on the TV launch pad, and it does turn. So I mean, I believe that does show every state of our Moore machine properly. You know, cycling through every state here does show this working. And so yeah, that's gonna be the end of the video, I think. I guess I should show that CECS.c, the built-in debugger. It's on 16 megahertz. That's why I have 160,000 here. Essentially, passing in an 800 for a red LED will make this go essentially go essentially it's 8,000 milliseconds. 8,000 milliseconds transfers to 8 seconds, which is the requirement of Project One. For a red LED, this same logic can be applied for the 600 seconds from a green LED and the 200 seconds for a yellow LED, which again, if you add those two numbers up, it adds up to 800, which is the total of 8 seconds for a red LED to switch to green. Yeah, so again, this number here is only because the debugger is in 16 megahertz. If we were in 80 megahertz, this number would change, which our board is technically in 80 megahertz. However, again, because the debugger is in 16 megahertz, we left it as this number here. But yeah, so that's the end of our video. And hopefully we just showcased a working Moore machine to as far an extent as we could without making this video too long. And a working code, the ports properly working, and again, the defines up here working as well. So thank you for watching.